Okay, so I want to go through, this is the agenda. Whenever we deal with a new subject and it's a bit tough, the first thing we try and do is to break it into little bits. So I'm going to start and break it into little bits, and we're going to break this into two types of loading. We've got isothermal loading and thermomechanical loading. Thermomechanical loading is where all the fun happens, that's all the difficult stuff. Isothermal is actually the simpler one, and in many cases we can get away with isothermal and make our lives easier. I'm also going to split it in temperature range into the creep and the non-creep ranges, because creep adds a whole layer of complexity. So if creep isn't significant, the job becomes much easier. So we'll split it in those ways. We'll then go on and have a look at some of the physics of high temperature fatigue and creep, and then I'll look at a few maths for the Bosch method, the Bosch creep and fatigue curves, and then we'll finish with some case studies, and then you'll probably be ready for your caffeine. So first of all then, I'm going to separate thermomechanical loading from isothermal. So when we talk about thermomechanical fatigue, we tend to think of this scenario. It's basically where the stresses in a structure are directly there because of constrained thermal expansion. So we're getting very high transient temperature changes. There's locked-in stresses. Some of them can be in phase. So as the temperature gets hot, then the material goes into tension, and that's nasty. The other one is if it gets hot and the component goes into compression, that's a lot better. That does a lot less damage. So phase is important. So this is the one that everybody tends to think, everybody dreads happening with TMF. It's where the stresses are largely due to constrained thermal expansion. And you usually find these on things like the hot end of the engine. So when you're looking at manifolds, turbochargers, things like that, these typically are driven by thermomechanical fatigue. Of course, if you're lucky, a lot of components, although they're at high temperature, actually are more traditional. So for this exhaust component, for example, the temperature here is fairly constant. It's hot, so the properties aren't great for the material, but it's a fatigue problem. The loads are there by mechanical means. It's a mechanical fatigue problem just exasperated by being at a high temperature. And when we get this, we can actually do some much more simple calculations, make our lives easier. So what is the physics of thermomechanical fatigue and creep? Well, temperature creates a lot of problems for us. We're all aware that if we take just a metal and take it to a high temperature, all of its static properties degrade. Its UTS reduces, its yield stress reduces, and that makes it a problem to design with, because whereas we very often like to design a factor of safety on yield, when we go hot, we very often can't do that. So materials really don't behave in a nice elastic way. They're very often elastic plastic. The other thing that we've got, though, is it affects the fatigue curve. So this is a typical sort of material which we use for hot components. And we can see the one on the right there, that's the room temperature one, 20 degrees C. But as we start to move the temperature higher and higher and approach the melting point, then there's a massive drop-off in fatigue performance. So temperature also affects fatigue. What's this creep then? Well, I've put a little illustration here. I'm using the Nabarro-Herring creep model here just to illustrate the effects of fatigue. But basically, if you imagine in your mind you've got a piece of chewing gum. If you've got your chewing gum and you load it, then over time it gradually starts to elongate, even under that constant load, until eventually it breaks. And what we're doing when we heat our material up, we're introducing the same sort of failure mode. And the Nabarro-Herring model explains it like this. Under very high temperature and load, then atoms that are on these high stress, these high shear stress faces, start to migrate. So the atoms in the material move down from these high stressed areas to the low stressed areas on the tensile plane. And the net result is that the whole of the material grains tend to elongate, and that's where we get this, this creep deformation. If you leave it long enough, then eventually it'll break, just as your chewing gum will. And that we call creep rupture. And that manifests itself, if we look at this tensile plane, then in the same way we get this atom diffusing. So atoms are now diffusing from these little voids onto the tensile plane. So these voids start to grow, and they coalesce and join together. And then eventually there's too many voids in there, so your material breaks, your component breaks in two. Now these little voids create problems when you've got fatigue as well, because these little voids can be initiation points for fatigue. And also fatigue cracks will actually exacerbate the problem of creep as well. So the two interact. And in addition to that, oxidation is a problem because, again, where we've got these exposed surfaces, oxidation will again increase the rate of damage. There is one little saving grace, though, in creep. There's a critical activation temperature that you have to reach. So in order for these atoms to physically move from here, you need to give them a lot of energy. And that means you've got to give them heat so they can vibrate. If you don't give them enough heat, then they don't really move. And as a rule of thumb, we usually say that if you take the melting point of a material in Kelvin scale and divide by 2, then as a rule of thumb, that's the creep activation temperature. Below that, there's just not enough energy to let the atoms move, so they don't. But above that, you can start getting creep. But it's not just a binary switch. Even at fairly high temperatures, you'll start to get creep occurring, but it takes some time for it to have a meaningful significance. So creep doesn't necessarily have to be a problem even when you're above that transition temperature. It depends on the duration of your loading as to whether you have significant creep coming in. Okay, so there's our creep. How does creep affect Fe as well? So we're used to, in a nice cold environment at room temperature, we're used to elastic analysis. So here's my simple structure. If I apply a constant displacement there, then I end up with a nice elastic stress in my spring. If I let go, it deforms back to normal again. At high temperature, then we may not be able to trust that elastic behavior, and so it can go elastic plastic. But again, Fe today is very easily able to deal with elastic plastic behavior. Takes a little bit longer than static ones, but again, it's not too difficult. If I go into the creep regime, then I need to use an elastoviscoplastic model in my finite element. So what this does is it adds a little dash pot here. So if I take this and I deform it or drag it down to a fixed displacement, initially all of that load turns into stress. But over a period of time, then creep alleviates that stress, so I get a reduced stress. And of course, if I start moving this, then I end up with the response lagging behind. So this is really what we're looking at with a very high temperature interaction from creep and loading. So that's a very short introduction to creep, really. Creep in 2 slides, I think, takes probably the record from most of the papers I've read. One thing is, whereas fatigue is always to deal with cycles, creep is static load, and tensile loads are worse than everything. But creep and fatigue will interact with each other. Okay, so let's classify these loads then. So we've got these 2 things. There's the steady state isothermal case, there's the transient case, and there's a temperature where creep isn't important and a temperature where creep is. And we can look at what types of analysis are best for each of these. So first of all, when we're looking at the exhaust system we saw earlier, then generally most exhaust systems fit in this nice area here. We may get away with linear elastic Fe in many cases because plasticity isn't significant in there. Of course, if we do get a bit hotter, then we may need to include creep as well. You notice, although I've got an example of an exhaust system here, I haven't really got any examples where we've got creep at isothermal. So if anyone's got an example, let me know, because I can put it in. But I've not come across anything myself where, and in ground vehicles, where that is a typical combination. When we're at the other end, so this is the transient cases, then we're typically looking here at things like cylinder head on the cold side, and we use a Bosch transient method. And I'll talk about Bosch in a second. So here again, the temperatures aren't really in that creep regime. To be honest, there are many components in a car engine which exist at this temperature range. There's a few up here, things like cylinder head, manifold and turbos, where in theory it goes into creep, and in theory we should be using elastoviscoplastic. But as I'll show you in the case study, in practice most components don't ever get that combination because the component where it's highly stressed doesn't necessarily coincide with the place where it's at a very high temperature. So what we usually find is that we don't often have a combination of the worst of both cases. Okay, so that's a little bit about the physics of creep. Let's have a look now at the actual, if you like, the SN curves for high temperature fatigue. So if we're dealing with an isothermal case, so remember this is a case where largely we've got static temperatures and a mechanical load, then very often what we do is we take the fatigue curves and we interpolate them. So within design life, for many years we've been able to do this with SN and EN. It allows you to take a temperature profile through the whole model and you can choose which temperature to use. And to be conservative, most people would choose the highest temperature. And then what we do is we interpolate the fatigue curves for that temperature and we can then calculate the fatigue. You can tell that's going to be quite critical because you've always assumed that the worst cycles occur at the worst temperatures. But it gives you a good starting point. Within this Bosch method and also the SN method now, we've built in the ability so that we can actually record for each cycle what the temperature profile was at each element on the model. And that enables us now to be able to work out the fatigue cycle by cycle rather than always assuming the worst case. Okay. But all of the methods are still based on a nest of curves and interpolation. So how do we deal with the cases where we've got transient? Well, this is quite neat, really. You see, normally we've got this nest of curves. Each curve is a different temperature. And what we do is we collapse them to an effective curve. So here I've chosen a room temperature curve as my effective curve. And what I've had to say is, what would I have to multiply the stress by here to make these points collapse on the master curve? So for each temperature, I actually gain, if you like, an amplification factor, a scaling factor. And what we do is we take the time history of stress and we scale those stresses up by the same amount, and that means when we do the fatigue we can rainflow count the new time history and use the master curve in order to work out what the damage is. So it sounds a really simple process, but it works remarkably well. So this is Bosch's process, but you'll find most thermomechanicals are based on a very similar process. Now the other thing was the Bosch equation. So first of all, if we look at this, a lot of people think this is an SN equation because it's got stress on this axis and number of cycles to failure here. But it's a local stress approach. Normal SN analysis in fatigue is nominal stress. But with this one, we use the Fe to calculate the elastic plastic behavior or the elastoviscoplastic. So in this case, it's local stress that we're using. That means that it's equally valid at low cycles as well as high cycles. So don't get confused. This is a low cycle method as well. Now this is the equation if anyone wants to look at the Bosch papers. Bosch is a very well-known French researcher who did all of this development work for Airbus on jet engines. Unfortunately, he likes to explain his equations in terms of differential equations, which engineers don't like. But if you're to expand this equation, you get something which is far more familiar to us. So this is the expansion, and let's just have a look at this. So when we look at this right-hand end here, sigma max minus sigma mean is stress amplitude. This bit here, the coefficient at C0, is actually the Baskin intercept, and this one beta is the Baskin exponent. It's actually the Baskin equation for Sn, really. The only difference is here is put in a modification factor, 1 minus b times mean stress. That, when you look at it, is actually the Goodman or the Morrow correction for mean stress. The only difference is, if this coefficient b, if you made b UTS, that would be Goodman. Or if you made b 1 over sigma f prime, that would be Morrow. What Bosch has done by allowing us to change that is to change the material sensitivity to temperature. Because one of the key things when we're doing stress-based methods is the mean stress. And the mean stress effects are much more significant at high temperature. So what this is it's using a very standard model, but it allows us to tune the effect for high temperatures where we get more mean stress sensitivity. If we move over down here, again we can see some parts. So this is effectively the UTS at high temperature minus sigma max. What this is the very low cycle fatigue part here, where we're tending to UTS. And similarly, on the denominator here, this is actually all to do with sigma low, and sigma low is tending to the fatigue limit. So this one equation allows us to have low cycle, high cycle. It's a Baskin type approach, and it allows us to modify sensitivity to mean stress as well. It really is a very neat approach. Just before we get onto the case studies, this is what we use for the Bosch creep model. So again, we do creep rupture testing. So these are the results from creep rupture tests, and we fit curves through them. And this is effectively the differential equation. This is the expanded equation. So what we're doing is we're fitting straight lines on a log plot through the creep data. And all we need to do to predict creep life is if we know the stress, we know the temperature, we can look along, and then we can get a rupture life in hours. So how well does it work then? Well, first of all, we did lots of analysis in the test lab. nCode operates a test lab in England, and that allows us to validate all of our methods before we end up giving them to the customers. So we did a lot of validation methods on this. And we can see here, these are normal lab specimens, and we get a little bit more scatter than what we'd normally see on room temperature, but again, it's not bad. And in fact, if we start to look at this in terms of error, we're typically looking here at error factors between 5 and 10 on life. So this is the raw material as a whole. Now this material isn't particularly good quality material. This is standard material that you would use in a hot engine component. So it tends to be inexpensive to buy. So you know, we expect this type of approach. So we're looking 5 to 10 times on life. Of course, this is just one temperature I've picked here. This is 600 degrees. If we have a look here, this is a combined set of all of the data we tested for this material at all temperatures under transient fatigue, creep, and variable amplitude loads as well. And you can see here that typically all of these are lying within a factor of 3 to 5. There's a few that are coming out to a factor of 10 on life, but again, we go right down here to very few cycles, 20 cycles to failure and things like that we're doing here. So lots of tests were coming out really within the expectations of what Bosch was telling us. Of course, the acid test is, it's all right doing 100 or so lab tests, but people want to see it done on a real component. So one of our customers helped us do some work. Unfortunately, they won't let us see their Efi results, so we'll have to just discuss them. But what we're looking at here is an exhaust gas recirculation valve. So it's very hot. We tested it actually with two different types of materials. One was a very high quality material, and the other one was a much less expensive type material. One creep wasn't really significant, and the other one we were well inside the creep regime. We've considered the analysis here to be both isothermal and transient, and we've considered creep as interactive or separate, just to see how significant creep is. So first of all, when we're looking at this, a good thing is to see, do you extrapolate beyond your measured life region? So we're finding within the stresses here, so this is the isothermal, our stresses in practice were all along this line here at this temperature. So actually, we're well within the measured data from the lab. We're not extrapolating it in any way. And similarly, the same one here, this is the transient, and again in the transient, we're well within that linear region in the lab. So what did the results come out like? Well, when we look at the Bosch isothermal, we were predicting about 500 temperature cycles to failure. Experimental tests gave us around about 1,000 cycles to failure. The Bosch creep, although there was creep at this temperature, we didn't have creep occurring in the regions of high stress. So that was a nice thing to have, but that is common with most engine components. The bit that is susceptible to creep is usually at the hot end where it's quite thick and the stresses are low. When you've started to narrow out the section and the stresses get higher, then the temperatures are also lower. So you don't usually get both failure modes coexisting at the same location. When we look at the Bosch Transient, then we were almost bang on. We were well within, in all the tests we did, was well within a factor of 2. One question that came up, though, was why was the isothermal predicting shorter lives? And when we started to analyse the failure modes, we found that this was because at the points where it failed, then the thermal cycles and the stress cycles were out of phase. So as the temperatures were getting higher, the stresses were going into compression, whereas the isothermal assumes worst-case conditions in both, and that's why that was giving us longer lives. So in conclusion then, as someone's just flagged me a 10-minute warning, and she's getting a 5-minute warning ready now. So in conclusion, we've had for a number of years the ability to do isothermal analysis with both nominal stress, Sn, and local strain, En. What we've added here is a new capability through Bosch, which is a local stress approach. So don't confuse it with Sn, because it's not nominal stress. This one is a local stress, and through the Fe, we're using elastic plastic or elastoviscoplastic modelling to take it to that point. We've also introduced creep models, and although I've briefly discussed the Bosch creep model, we've also implemented the Larson-Miller creep model because that's the one that most people will be familiar with. When it comes to true thermomechanical fatigue, then we've got the Bosch combined creep fatigue model, which I've briefly illustrated in picture form for you. And when it comes to doing the finite element analysis, it supports linear elastic, if you're lucky, elastic plastic or elastoviscoplastic. A lot of people, when we started this, immediately thought, well, everything's got to be EVP because we're in the creep regime. Actually, we've found the opposite. In most cases, even on the very hottest of engine components, the stress cycle effectively doesn't exist for long enough that creep has a significant effect. So if you're very close to the melting point, then creep is a problem, but we tend not to design components that long. But also, the startup shutdown cycle is quite short compared to the creeping, the amount of creep that's occurred over that time. And so very often, you know, an industry as a whole, we've got away with it for so many years because in reality we don't get an awful lot of creep even at the high temperatures, which was a nice thing to find out because that's how we've been designing things for so long. And it's nice to know that the old engineers didn't get it wrong. Okay.